yeah, so I don't know whether whether the Milky Way thing's fad has quieted down a little bit, or whether it's just the weather. As a couple of years ago, it seemed to be peak Milky Way, and it maybe is. That's really nice there. The sun's picked out the dark lines there particularly well, and I've had some fun with Jupiter. I've seen a couple of people who've been getting their gear together and getting some planetary stuff done, who, while they're still relatively new to it and starting, I see people improving all the time, and everybody here is very much up for helping. One thing I was thinking of doing was possibly next month, because it's still the middle of planetary season, and I brought it up on the Facebook page and people like the idea, which is people bringing in their laptop and their own videos from their cameras, and we run a real sort of group workshop where we all sit around and help each other get through from here's a video straight out of Shark Cap or whatever, all the way through the stages to getting a really good result at the end. Because I know some people have got perfectly good data and they're not seeing the results at the other end because they're missing some trick. And there's no substitute for working with some people who have been working with it, and there's few people here who are pretty cognizant of what to do with this stuff. So yeah, nice to see people's gear out there. So yeah, I'll hand you over to Jonathan, who's going to run us through tonight. I brought a couple of assorted filters. Andrew's brought a bunch of filters that people can have a look at. There is the Optiline ones. I've got a couple of filters with me as well.
I'm covering most of those in the talk. So
and talk about them, including some fairly, I think Andrew probably wants to jump in at the end and talk about a couple of products that are coming out as well. There's some interesting ideas and filters coming out with multi-band, effectively multi-narrowband filters. Seems like quite productive possible avenue for colour camera users. So yeah, if you want to grab the HDMI cable over and go ahead, Jonathan, and thank you very much for your effort preparing for this and taking over for a month. And okay, cool.
it's going to be able to see which is more important than the dark.
Do you need a torch?
Yeah, I think it'll be right.
Do you want me to move my laptop so you can put yours up there?
I think it's the tech.
Doesn't really matter. I just need to make sure I'm actually connected. Usually it's usually functional this one, isn't it? Hold down function, press that. Should see the mouse. There you go. Now you switch probably it. Go to Jupiter probably easiest. No, it didn't register the clock there. Oops, ah.
Oh, there you go. Good.
I'm a nervous moment.
And we're online.
We started at the beginning of it. Right, hi.
Hi.
Hi, my name's Jonathan Davey. No, I thought I'd do something just a little bit different tonight. And I thought I'd tell you a little bit about myself, sort of an icebreaker, and then a little bit about what I do, why I do it, and how I do it, just for about 5 or 10 minutes. And then we'll get on to the light pollution straight after that. So this is me, Jonathan Davey, born Exeter, England, so I'm an immigrant. 4th of May 1960, so I had a Star Wars birthday. May the 4th be with you. But I didn't realise that until I was 18. Because, I didn't realise that until I was 18 because that was my 18th birthday and that was the first Star Wars day because Star Wars was released in 1977, but that's wasted on me. I'm not a Star Wars fan. So I'm a retired food technologist, so I have a little bit of basic background in science, but nothing in physics, nothing in astro, nothing in astronomy, or not even any prior experience in photography. My other interests are my 1973 Norton Commando, which I've had since I was a teenager. My favourite retro music is Deep Purple. I love skiing on Mount Ruapega, and I must take a telescope up there one day with lovely clear skies. I'm married with 2 grown-up girls, and this is the love of my life. No, that's the wife. That's the love of my life. Which I've combined with my favourite group, Deep Purple, to make a Deep Purple Norton Commando.
Nice.
What's this got to do with astrophotography? Not a lot, except Deep Purple released the track Space Trucking, which was the wake-up music for one of the space scientists on the International Space Station, but unfortunately she didn't make it back to Earth because she was on the return shuttle to Columbia, which went off on the entry. Okay, that's just a quick icebreaker about me. So on to my astrophotography. So why do I do this? For some evenings it's more like, why do I do this? So from a very young age, my father would take us outside, look at the sort of the new satellites going across the sky, which is quite very few of those days. I didn't do a lot as a teenager, apart from having a look at the Jupiter and the moons of Jupiter through a pair of binoculars. But in 1986, I bought a telescope so I could see Halley's Comet. I went out to a dark sky site and saw this really faint, fuzzy grey patch, which was very unimpressive. So didn't really do much from there for quite a long time. So I emigrated in 97, moved to Aremu in 98, so I've been there 21 years. And I thought, wow, these such great views of the Milky Way up there. What's that little fuzzy spot to the right of the Southern Cross? And it was only when I joined this group that I realised that was Eta Carina. So I attached my first digital camera to a cheap Newtonian in the very early days, and I got a really, really great image of the moon. Oops, sorry, people flicking back. I got a really great picture of the moon, which was completely white, completely uniform, and had no details whatsoever. So that was kind of a bit of a flop, so I decided I needed more time and more money, which is when I retired, I thought, right, I've got the time, and luckily I had enough money, so I thought, right, I'm going to get on with it now. So this is where I am, Aremu. I can't really see it on the screen, I hope the pointer would work. So, south of the city, sandwiched between the Hinua Hills and the motorway. And so I've got the sky glow to the north, and I've got a bit of sky glow towards the motorway, but the south, so I've got a great view of the Magellanic Clouds, Tarantula Nebula, Eta Carina, and also to the east is really good, so I've got the Milky Way rising, which is really quite nice. So I'm quite lucky where I am. And I'm in probably Bortle about 4 now. I think it was probably Bortle 3 when I got there 21 years ago. And no doubt one day it's going to be Bortle 5 with the rate of glare from the southern motorway at the moment. So this is the view from my house. So nice view over the Hinua Hills. And you can see on the left there, I've got my tripod. I've just migrated there from a tripod to a pillar. And the pillar there is separated from the deck, so that I don't get any vibration when I'm moving around the deck. But as Sean pointed out to me, I don't want to fall off the edge of that, which is always my plan, was to build a frame around it, make it waterproof, so I'm not going to, so it's not going to get wet. So that's as I was building it. You can see there I've got I've got an AZ EQ6 mount, which I only use in equatorial mode. I've got the Astron Z4 Newtonian on there, so it's giving me good wide field images, deep sky images, and that's where my starting point was when I started. So I put a roof on it and put some walls on it, and there you can see it's sort of bolted in at the side, stop it flying off in the wind. And right at the end you've got an extension so that I can just slide the roof back. There I'm sliding the roof back, nice and light, polycarbonate roof. And there you can see my other telescope, which is a Meade ACF 10-inch scope, 2.5 metre focal length. So that's it's got the planetary camera attached there. A massive cables, which I've learned is a good idea to use some cable ties recently. So I've managed to tidy that up a little bit. So that's kind of where I am at the moment. So that's it, AZEQ6 mount. I use 2 cameras. I've got a Canon 7D Mark II, which is quite nice low noise. That's an APS-C crop sensor and unmodified. And I've got a Canon 60, which is modified, which is a full frame sensor. But I found that I can't get really good crisp images across the whole of the full frame sensor when I'm using if I use the Meade with a focal reducer, the edges tend to be a bit distorted, and if I use the Barder MP3 coma corrector, it still doesn't fit the full 60 frame on the Newtonian. So I really struggle with getting crisp images to the end of the frame on the full frame sensor. Great breakthrough for me was when I got a Sky Safari Bluetooth device. Prior to that, I was finding nothing in the sky, just using the standard SynScan controls. But the Sky Safari with an app on the phone, and I was zooming around the sky, seeing everything I wanted to. That was a real breakthrough. And my new addition now, I've got a pillar. I don't want to take my mount off there because it's perfectly aligned. So my new idea is to get a portable mount. I've got an AZ-EQ5, and I'm going to get a Mac Newt scope to go on it, so I can take that around in my motorhome and take it wherever I go to the sky sites. And onto the filters, I'm currently using a UHC and a Duo narrowband filters, which we'll be covering soon. So that's just a little bit about me and what I do. I always wonder what other people do when I come here, so I thought, right, I'll stand up and I'll talk about it and I'll do that, in the hope that other people do that. I know quite a lot about what Sean does, and I know a bit about what Liam does, but most of the rest of the people haven't got a clue, so I hope you find that interesting and you're inspired to do something similar. So yeah, give it a go. Thanks for listening on to that, and now I'll go on to the light pollution. So in order to understand how filters work, you really need to consider what the spectra is that we're trying to capture. So be familiar to most of you, I'm sure, but I'll just sort of cover it so it's very clear what we're doing. We've got the hydrogen alpha at 656 nanometers, which is most dominant in the star-forming regions such as the Orion Nebula and Eta Carina. Now it's very important that these are emission nebulas. They're sending out light from the actual elements straight to our cameras, and which is really what is great to be able to pick up. And you've got hydrogen beta, which is a less strong signal than the hydrogen alpha, I believe, and that's very close to the oxygen spectrum line, the oxygen 3, which is an emission line which is in the blue-green, whereas the hydrogen alpha is in the red part of the spectrum. Then we have the sulfur 2 line, which 672 nanometers, is further to the right of the hydrogen alpha in the red part of the spectrum. Now that is generally quite a weak signal, and it takes a lot of exposure time to get a decent result on that. So if you're doing bicolour filtering, which is something that I'm dabbling with at the moment, that's typically left out, but it's included if you want to fully recreate a Hubble palette. So when we're doing the light pollution, we're always thinking about the actual light pollution being a signal, but it also contains unwanted noise. So if you're comparing being in a rural site to a city light site, obviously your sky pollution increases, but the signal from your target is staying the same. So as the light pollution increases, you've got a greater problem with removing that sky. So you've got a greater gradient. Now that gradient can be removed in processing. For example, the Pixin site, the dynamic background extractor, which I think Liam showed a few months ago, is a very good tool for doing that. I'm not sure what the options are on Photoshop, but certainly from my experience, the dynamic background extractor is incredibly effective at removing background gradients such as the sky pollution. Now we're also left with noise, and that can be removed or that can be reduced, but not completely removed. And you're going to get better results if you've got more stacked images or a longer total exposure time, I think is the most important thing. So the noise reduction processes are generally used on the fainter parts of the image, and you'll be using sort of the normal techniques that we all use for that. So what are the solutions? Now I'm going to go with the obvious solutions, drive to a dark sky site, because there are just some things that you probably won't be able to do in city lights completely as well as you could do out there. But the problems are we've got a distance to drive, at least in from Auckland. You might be in the middle of nowhere, which isn't a nice experience necessarily. You could go to see family and friends. You could go to family and friends or go to more star parties, but there are some disadvantages. You need a portable lightweight mount, you need to do your polar alignment, it takes quite a long time. You need power, probably a heavy duty battery, and of course if you're planning this in advance, you're at the whims of the weather forecast. Next option is to do more subs, more processing, noise reduction, etc. But if all of those don't work, then, or not options for you, then you're considering considering the filters. So I've got 3 classifications of filters there. You've got the general light pollution filters, but you've also got the options of LRGB mono camera filters. Now, I believe that this actually is a benefit in light polluted areas. Any comments on that? Do you know? I don't know much about that really.
I just know that with the mono camera, there's no benefit to using a light pollution filter because the red, green, and blue filters are broadband, and that's the reason why you use them. You want that broadband data.
Yeah.
Filters just filter out the signal that you want.
And when you went from colour to mono, did you find that you got sort of reduced light pollution issues?
I still deal with gradients in my broadband data. But
Yeah.
it doesn't reduce.
Right,
light
doesn't
pollution.
reduce it that much. Okay. Yeah. So if your normal light pollution filters aren't working, then you can go to narrowband. So they are effective for all types of light pollution and moon glow. And I think these are becoming more popular. But they do require longer exposures, and you may need to be doing more guiding. So those are a couple of drawbacks with using the narrowband. So using filters, they're useful for the emission nebulae in particular. So as I mentioned before, the Orion Nebula, Eta Carina, and the Rosette have mostly oxygen and hydrogen emission lines. And the filters are much less useful for reflection nebulas such as the Tamariki Pleiades, for galaxies, star clusters, and all these are broadband emitters. So when it's broadband, they're not so effective. When you've got higher levels of light pollution, generally speaking, you're going to need a more restrictive filter. Using a filter, as I said before, reduces the signal, so longer exposure is required, and you'll be needing more guiding. So here's an example of a typical filter. This is pretty similar to the L-Pro, but I've got all sorts of different spectra shown on here. And I thought this was particularly good because you can see the different colours across the spectrum there. So you come from, it allows some blue light through, it's got a dip where it's filtering out mercury line. The mercury line isn't particularly relevant for us because we don't really have mercury lights. Then you allow more blue light through. You've got the hydrogen beta and the oxygen lines. The left-hand line is the hydrogen beta, and you've got two oxygen lines. Then you're filtering out the mercury line, and this particular one's allowing some green through, and filtering out all the sodium light in the middle, and then you're allowing through the hydrogen alpha and the sulfur to the right. So these are the types of classifications. That one there was a multi-spectra type filter, which is peaks and troughs, allowing most of the broadband signal through, but filtering out all the traditional light pollution. That's important to say traditional light pollution, because LEDs are a bit different. So these are similar to the Optron Pro, and there's one of the main ones which seems to be very popular is a VTech IDAS-1 LPS light suppression filter. Next in the list is UHC filters, ultra high contrast. So these filter out more of the broadband light, but still allow the oxygen and the two hydrogens and the sulfur through. Next, the other one is CLS, which stands for City Light Suppression. Now this is somewhat in between the multi-spectra and the ultra high contrast, and I've had examples of all of these three for you to have a look at. And then lastly, we've got the narrowband, which is good for all light pollution. Now you can either have single element filters, hydrogen or oxygen or sulfur. You can have duo-band filters, which combine the hydrogen and the oxygen in one filter, and I'm currently using an STC duo-band. Or you can have tri- and quad-band filters covering the hydrogen, oxygen and sulfur, and or hydrogen beta. So there's quite a few different options there, getting generally a lot more expensive to the bottom. I think some of the top-end ranges are sort of like $1,500. Quite expensive. So we need to know what we're trying to filter out. So the biggest problems that we have, and I'm making the assumption in all my charts here, that the problems that we have are high pressure sodium and LED lights. There will be a few low pressure sodium lights around, maybe some fluorescence, maybe some mercury, but to be quite honest, I think they're so few, and I think they're all going to be replaced with LEDs. And there's probably negligible and no use of metal halide, incandescent and halogen. There might be some metal halide, I think, where you've got stadium lights, so that might be an issue. So I've tried to find out what Auckland's doing on the internet. I haven't spoken to anybody, this is just like readings from the internet. And until recently, most of Auckland was high pressure sodium lamps. But there is a plan to replace all of these by LEDs by 2025. So there was a 5-year plan in 2014, which I presume they've just about finished, so we're probably about halfway through, changing them all over to LEDs. And there's another 5-year plan in progress to do the other half. So we should be assuming that most lights will be LEDs in 5 years' time or so. LED lamps, the ones that are used in Auckland, I believe, are designed for low scatter, so they've got reflector hoods over the top. So that's one advantage which is working towards us, so they're directed downwards, and they're dimmable and centrally controlled, which means they can reduce the light or turn them off at certain times. So hopefully they'll reduce them when we're doing our late night astro. The types that they're using, they're currently using 4000K LED white blue lights, and it would be better if they used lower temperature LEDs, more orange. There is one particular one I've read about recently which is called a narrowband amber LED, and that's no worse than the current lighting, but for certain reasons they're going for the higher K, which is probably not very good for us. So on this chart, you've got at the bottom, you've got low pressure sodium has a sort of an equivalent value on light pollution of 1. High pressure sodium is probably twice as bad as that because it's slightly wider spectrum and less sort of clear lines on the spectra for the high pressure sodium. But LED lights are considerably worse than either of those, going up to 8 times as bad. Probably what we're going from high pressure sodium at a scale, on the scale of about 2, going up to mid-white LEDs going up to about 6. So we're probably going to be 2 to 3 times as worse off on light pollution than we might be in the first place. So this is a graph of the LED light to give you an idea of what we're trying to deal with. So the line that we're really looking at for Auckland is the black line. So it reaches a huge peak at the line of 450 nanometers. Then it dips down quite good for us actually at the 500 line, which is where we've got the oxygen lines and the hydrogen beta. So if you're using a narrowband, that's going to be quite good. It then goes up to a more broadband peak before coming down again before you get to the hydrogen. So if you're going to be using narrowband filters, it's probably going to be quite good for that. On this graph I was reading that they put the blue line in there, which is kind of the equivalent of what moonlight is, because there is a theory out there that they went for the white LED lights because it's more like moonlight, but apparently this is completely fallacious because you've got that huge peak at 450 nanometers, which is totally unlike moonlight, much more blue, and of course these LED lights are a hell of a lot brighter than the moon is.
The reason that it was chosen at the time the spec was written by Auckland Transport for their options, that was what was economically feasible. Because the deciding factor of the change of it is the money they're saving energy, much as all the other benefits or not benefits. At the end of the day, what's deciding is the money they're going to save.
There is another theory that the white and the bluer light actually is a better light for seeing things. So like if you're trying to look at somebody, you get a little bit more facial recognition.
Money they're going to save on energy.
Money, yeah.
At the time, 3K lights were the technology level that could save the same sort of money as the 4K lights. But we did get 5K lights, which was the difference.
So here's where we are with the high pressure sodium. You can see all the peaks there are between 500 and 600. And really the biggest problem with the LED is the sort of the high peak at 450 nanometers. Now I put the mercury light in because on lots of the filter specs it shows the mercury lines. So you've got lines at 435, 545 and 577, and they show up on a lot of these graphs, so I just thought I'd put those in so we know what they are. So again, here is that STC optics, just to familiarise ourselves. So we've got the 2 mercury lines, which probably aren't important, but the main thing for us with high pressure sodium is that we've got that between the 550 and the 600 where it's got the sodium there. But at 450, that's probably allowing through a lot of LED light. So that's not really particularly good for the future. So here is the Optolong L-Pro. I think I did see 2 versions of this, but I didn't really know which one was whether there was significant differences, but this did seem to come up quite frequently as the spectra for it. So here you're allowing through some, on the left hand, going from left to right, you're allowing a peak just after 400 meters, 400 nanometers, you're allowing blue light through. You've got that's the mercury line, the first line that's there, it's filtering out mercury. But you do notice that at the peak of the LED at 450 nanometers, the Optolong L-Pro is allowing through quite a lot of that LED light. As you go through, you're allowing through the hydrogen beta and the 2 oxygen lines, and then it's got quite a clear gap before allowing through a lot of green light before it filters out another mercury line, and it's allowing through some more green light and yellow light, filtering out the sodium. Then coming back up again for your hydrogen and your sulfur lines on the right. Now this is the one that I ended up buying about a year or so ago when I started to sort of think about this before I'd done a lot of research, to be honest, so it was a bit of a guess. But I did notice that the 450 nanometer line for the LED, that does come in a little bit after that, so it's probably filtering out a little bit more of the LED lights than the L Pro does. It then comes in, it then cuts down pretty quickly after the oxygen line, so it's cutting out more broadband green light after that, and then filtering out all the other, anything else in between before it's allowing through the hydrogen and sulfur again. Now this is just a comparison in case you're wondering what's the difference between a UHD and a CLS. Pretty similar one on first glance, but when you have a good look at it, the UHD comes down very quickly after the oxygen line, after the third green line, whereas the CLS comes down a little bit later, allowing a little bit more green light through. So that's slightly more broadband light, but not a lot of difference really. So that's just a quick comparison of UHC versus the L Pro. You can see the L Pro's got more broadband, and the UHC is much more restrictive. Now this is a new one that I was just talking to Andrew about, and he's just heard about this. We don't have stock here, I've seen stock in other places, and prices on it look not too dissimilar to the L Pro. But this is really, in effect, it's pretty much a duo narrowband. So you've got, it's covering the hydrogen beta and oxygen all in one peak. So it's almost like having 2 narrowbands together. And then it's got a narrowband on the hydrogen alpha. So it looks like a pretty useful combination. This is a filter I bought before I found out about that one. I worked out, I found the STC duo narrowband about 6 months ago, so I bought one of these, started using it. So it's got the oxygen and the hydrogen alpha, but it's got a little less of the hydrogen beta. I'll just show you a range of other filters just to give a real idea of what the range out there is. This is a HITES 1, which is pretty similar to the L Pro, and that's cutting out the traditional light. But their new filter, they've come up with a new generation filter, the LPS D2, and you can see on the left-hand side the blue LED light. They've made a particular cut out that particular peak 100%. So that's quite a good modification, and that might be, if you still want to go for your sort of your wide views of the of the Milky Way.
You still forward about 10 pictures.
I'll just go back to so if you're doing a picture of the Milky Way, you probably don't want to be using narrowband because you're going to cut out all your stars. I'm going to go through these. Yeah, so you wouldn't want if you want to take pictures of the Milky Way from the city, this is probably your best bet because it's allowing more broadband through and cutting out as much LED as you possibly can. Here's an astronomic CLS, so clear city light suppression. And the interesting thing about this, so it's allowing light through from 450 to 550, which is pretty similar to most CLSs, but on this one it's interesting that they've sort of carried on past the 700 nanometers and sort of almost indefinitely, so probably allowing a little bit more infrared through. And this is an astronomic UHC, so we're getting into the sort of more technical filters here. And again, it's got a pretty narrow band on the hydrogen beta and the oxygen, and it's allowing the hydrogen alpha and the sulfur through, but it's also showing you that you've got quite a lot of infrared. And this is one area I haven't really been able to find out much about, is that some people say if you want to take pictures of galaxies, you know, with a bit of light pollution, you're going to have to be having a bit of infrared in there, and it's going to depend on your camera. So I don't know if anybody's got any experience in this area, but it's one area where I haven't really been able to read much up about it, the infrared spectrum. So that's the Bardit. Now I'm not sure how you say this, neon, bit of a tongue twister. I think this one's used more for taking pictures of the moon and for the planets, and less so. It does say it's a sky glow filter, but it's obviously letting in all the LED light, so it's not going to be much good for us or for that particular purpose. Here's a Lumicon. Again, it's allowing through the hydrogen beta and the oxygen, allowing through the hydrogen alpha and the sulfur, and it's got a lot of infrared coming through as well. This is an interesting one. I couldn't work this one out because it's narrow band for the hydrogen beta and the oxygen lines, but it's filtering out hydrogen alpha. I don't know what the idea is there.
Are they trying to balance it so that, because hydrogen alpha is that area of the camera is more sensitive a lot of the
Can be
time,
very dominant, so
and
yeah.
stop it so you can, it's an attempt to balance your exposures.
This just shows that not all UHC ultra high contrast filters are the same. So
No.
if you're thinking about buying a filter, make sure you've looked at the spectra for it before buying it. Make sure it suits. And this is just one. I read one technical article, a bit beyond me, but they had actually sort of done the performance on infrared for galaxies on filters and rated them from the top to bottom. So the astronomic CLS was the best. But again, I don't really know much about that. So that's pretty much. I started off a year ago, knowing nothing about filters, thinking I want to find out about it. So I just trawled the net. This is my summary. I hope that's of some use to you. And these are just my pictures, just to give you some idea of what you can and cannot do with them. So this is my duo filter. That's the Herschel's Ray or the Pencil Nebula, which is part of the Vela Supernova remnant. This is the Eagle Nebula with the duo again and the modified 6D, which is showing a lot of fine detail. I haven't done the processing particularly well on that yet. Need to go back to that because there's some good data in there. Now this is a picture I took last year of the lagoon with the 16 modified camera, but without any filter, prior filter days. And that was put into the astronomy book, the yearbook. But I lost all my data because my laptop died, and my backup laptop died at the same time, so I lost all of them. So I just took a picture of it just to show you what last year's picture looked like. You've got a lot of reflection at the bottom, which wasn't there. But this is to show you exactly the same exposure, but with the duo filter. Looks like that, which has got a hell of a lot more detail, a lot more contrast. And yeah, with the emission nebulas, it really seems to make a difference. So great for emission nebulas. But what it's not so good for is for your galaxies. So I've been doing M83, like similar to everybody else at the moment. Great time to be doing it. So this was no filter, single image, 5 minutes. Obviously with guiding. It looks like a hell of a lot of background sky glow there. But would be worse in the city, I'm not too bad. But processing that in PixInsight, I'm able to make it look like that. So processing can do a hell of a lot. And I think you should investigate processing and PixInsight or the equivalent Photoshop methods, because probably just for that, PixInsight is probably worth buying in my opinion, just because it did such a good job at reducing the sky glow. I haven't even done sort of significant noise reduction on that at all. Whereas if you're buying a filter, you're probably spending several $100s on a filter, so probably worth giving the software a go first. I've done the same image with the UHC filter. So you can see pretty good on the sky glow, not much sky glow, but the image is, the actual signal is starting to diminish, and I didn't do so many subs on this, but when I process it, I don't get nearly such a clear image. And if I go to the duo, I didn't think this was going to be very good, but I tried it in case, and that's what you get. Pretty much rubbish really, and the image is probably the worst of the lot. It's showing some interesting red patches, but the rest of the broadband is all filtered out. So that's my summary. Dark sky is best if you can get there. Filters are good for your emission nebulas, less so for reflection nebulas in galaxies and your broadband targets. You may need to increase your exposure to increase your signal to noise ratio. You need to increase the filter strength as the pollution increases. And I was quite happy with my decision to buy the UHC a year ago. That came up with some good images. And the narrow band for emission is good, but can be quite expensive. Although this new one for a Mach Long looks like it might be quite reasonably priced. There are more options out there, and the prices do seem to be coming down a bit for these duo filters. So that's my experience. I hope you find that interesting. And any comments or questions?
There's also a tri-net filter coming out, I believe, that allows S2 or 3 and HA.
Yeah, you've sort of got the tri-band filters. I think some of those are available. I've seen them sort of on the American website. Some of those are $1,000 plus, quite expensive ones. But I've had the duo.
If you've got a reasonably good quality colour camera, if you haven't got a mono camera, I could see the tri-band filter being a bit of a, you know, if you've got a colour, if somebody's bought an AS16 with a colour or something, or they've got a modified SLR that works particularly well, then that filter, I guess, could really make a huge difference.
Yeah.
But yeah, conflict. If you've got a modified camera, waste of time because your self alarm just isn't coming through anyway. If you don't know if anyone knows, but if you've got an unmodified SLR, you're not getting anything really in sulfur.
Yeah.
The camera's just not capable of picking up that light. If you have your SLR modified, then the self alarm comes back. So that's quite a thing. But yeah, those, as you said, those trigger filters look so far very expensive, but there does seem to be hope for some of these filters getting a lot cheaper, and I don't think there's probably any really good solid reason for them to be so expensive. I think it's just that they're new. It's a new idea, so people are making the most of it until everybody's got one out there, and it all has to come down a bit more reasonable.
So from my perspective, so as we sell the optical filters, my biggest kind of thing, which is working out what I stock in the model, because there's so many different options, and I don't stock the CMS ones. I need to know so quite popular with the older ones. The UHC ones have been very popular. The L Pros, not so much money because they're twice the price of UHCs, more expensive. And the new L Hunts, I think, and Saturday was announced last week, so I don't know the stocks out of the moment. I need some next month to try it anyway. But what I'm interested in feedback from you guys is what sort of filters do you want? Because I do a lot of filters in stock already. I bought some over to play with, show and tell. But like we have even the narrowband filters we have, the CC grade ones. What would you be interested in? What do you want in stock? Always just that feedback. The other one is to buy the time by quantity. So I don't know if it's buy two other filters at one time.
I'm sure lots of people got warehouses full of colour filters nowadays. Really not fashionable the way they once were. There's an awful lot of them sitting around that nobody uses. It used to be when now astrophotography has become so popular and visual in some ways less so, that you just don't feel aren't using some of the filters they used to use. But yeah, you definitely don't want to be buying in that stuff. Nobody's going to buy. The L-Pro, I think, was A, it's been expensive, and B, it is more of a, it's great. So I think it's probably a great filter for some of the Milky Way photography. On marginal areas for Milky Way photography, it lets you do Milky Way photography you just wouldn't be able to do. But for the actual deep sky telescope stuff, it's a bit broadband. It doesn't. It does work, but it's not. I would say the UHCs and the CLSs I've used give you more oomph in terms of killing the background. One thing that is, I think a PixInsight probably does a lot better. Photoshop, you struggle in Photoshop with is the CLS filter certainly is colour balance.
Correction.
You end up with very strikingly blue-green images. Your first reaction when you get a CLS, you buy a CLS filter and get the image off the camera is horror. That it's producing this horrible monochrome blue-green image. In actual fact, there's a lot more there, and you can once you start personally, you suddenly realise there is data there, but it's that's
the PixInsight is very easy to use for colour calibration.
PixInsight has
really automated.
Much more mathematically sound colour calibration. I mean, I would definitely agree on the basis I'm going to be buying PixInsight in myself. I'd agree with both Liam and Jonathan on this, that PixInsight at $400 or whatever is worth more to you than a $400 filter is probably going to be as an investment in astronomy.
It's a long-term investment, that's for sure.
It's going to do all your images forever, as opposed to being a particular purpose. So it does seem like that's definitely the way to go.
It's a very steep learning curve with PixInsight. I mean, I've really struggled on the first 3 or 4 months. It's difficult.
I've found that with people who are using it, giving a few talks and information, it's not as bad as it seems.
No.
Once somebody's showing you through this stuff, it's not a horrible nightmare. I found once I tried it through the trial, and I definitely found the calibration and stacking integration side of it was probably easier than doing it what seemed like the simple way, your deep sky stacker and stuff. Once you've got the process, it does a really great job, and you don't have to muck about with it. It's very systematic. So once you've got it set up, I think that's a big deal there. And then somebody else said they got some slides they would want to we're going to maybe plug in and show up that you've got.
I've got time.
Got a few minutes, so still got another 15 minutes of time left.
I did get pricing for the Yellow Hunts ones on Friday. The 1.25 inch is going to be basically $300 and the so $300 and the 2 inches $100.
You could clip in.
They said it's a limited quantity available.
Yeah. So we put in,
I mean, not for everyone, but
if you're doing telescope, I have to say for my experience again, for doing actual telescope work, I prefer screw filters than I think the clip-ins are, it's much more, try and put a clip in the dark.
One interesting thing I read about the two types of filters, if you've got the filter on the end of your, sort of far up the optical tube, and you're still focusing, after that you're going to get more sort of defocusing. It's not going to focus as well. If you put it in the, you've got a slot in the just in front of the sensor, you're going to get less distortion.
As far as I know, I don't. If you're putting a 2-inch or a 1.25-inch filter in, you're generally putting that. It's the camera side of the focusing mechanism. You know, you're never going to have it the other side. I have to. I have a brief experience with that because I own the. By accident, really, I ended up owning the Celestron filter, which I couldn't tag there, it's an amusing thing because it looks like looking for a black solid clad glass. Celestron did a light pollution filter, they called it the LP filter, I think, for the C8. This is back from the 1980s probably, which screws onto the actual back of the image cell and everything else goes on after that. And I found that thing is just, you get almost no light through it. I'm not quite sure what. They really wanted to kill the light pollution, so they killed most of the images as well. I didn't pay for it, but yeah, it's a bit of a beast.
I bought a clip-in duo because I wanted to use it with a lens as well.
Well, that's the other thing. If you buy a clip-in, you can use it for with a lens. And increasingly, people are doing deep sky photography, deep sky work with a lens, of course, because with sky trackers and all these things, you can do long exposure 500mm lens and 300mm lens and do the Milky Way centre, and you're into deep sky territory rather than artistic territory while still using a lens. So yeah, that is a big advantage of clip-in, of course. There is also a whole world of filters out there from the photography world, of actual camera filters. And some of them are kind of light pollution filters and stuff, which they feel live in their own world away from astronomy, and I've read a few articles where people are comparing these filters, and some look like they might actually be quite effective and possibly quite a lot cheaper, but there's very little information out there in terms of astronomy for them. You know, they've been made over the years they live in the photography world, so there's some quite, I think, more popular in the States where that market's a lot more developed.
yeah.
It can always be a problem here, of course. It's very small.
Yep.
Go on, sorry.
Okay, I'm Tony Cooper. I wanted to understand how these filters work, so I bought a Bada UHC filter and then I played around with it, and this is what I'm doing. So this is taking a photograph of a colour checker in white light. I used an LED for that, and this is what it looks like. Then I took it outside and photographed it in sodium light, high pressure sodium, which is orange, kind of looks orange. And then I took the two images and I subtracted the sodium image from so then I took a photo of it both in sodium light and white light. So that's, and then I subtracted the sodium image from the white and sodium image to see what was left over. And I got back to the original. So the top one is the original, and the second one is photographed in sodium light, where I've subtracted the sodium image. And that was quite interesting because it showed that you could subtract two images, one of which had sodium light pollution, and get pretty close to the original image. So this is what the UHC filter does. It takes all of that and just passes those ones. And so you can see the effect on the colour checker. This is the colour checker in white light, and this is it in the UHC filter. You see it changes the colours significantly sometimes, some of the colours. So photographed the image in sodium light with the filter and without the filter. You don't? No. I photographed it in sodium light. Yeah. Anyway, the images with the sodium light was the same as the image with the LED, with the white light when viewed through the filter. So this is the image with white light through the filter, and this is the image with white light and sodium through the filter. So they're the same. So it shows that the filter is effectively removing the sodium, which we kind of knew that it would. I just wanted to see if it would. And they're very similar. You can't tell them apart. So it's doing a good job of removing the orange. But that's not the way that astrophotography works, because you can't photograph nebulae illuminated with sodium light, because our sodium lights aren't strong enough, and it's a long way. So what happens, so what I wanted to do next was I wanted to simulate sodium light as light pollution, and I don't have a sodium lamp. So what I did was, got the telescope, I put this colour check against the wall, then I got an angled piece of clear plastic and put a sodium light, put a compact fluorescent light down here, so that the image from the colour checker came through to the camera, and in front of it superimposed was the fluorescent light coming through. And that's what the compact fluorescent spectrum looks like. The important thing for us is that there's a lot in the green, and there's a lot round about where sodium would have its orange. So it's adding two light polluting elements, probably maybe a bit of blue as well down the other end. So this is the colour checker in white light. This is the colour checker in white light, but viewed through the plastic. So it's clear plastic, but it's not glass quality, so I had to take an image through it. So it's a bit blurred. That's okay, the colours are pretty much identical. Colours don't change just through the plastic. That is the compact fluorescent light by itself. And you can see that it kind of looks like Auckland pollution.
Yeah.
So it's pretty good simulation. Nice move. This is both the white light and the pollution. This one, I subtracted the pollution from the image with white light and pollution, just as I did before. And you can see that I almost restored the original image. So I concluded from that that perhaps subtracting pollution in software is a pretty reasonable thing to do. And I did the same thing again as I did before, so I'll skip those. This is the colour checker with the filter, and this is the colour checker with the filter and the pollution. So you see the pollution, it's not quite the same, the pollution did add, but the pollution wasn't uniform. So what we had is an image through the filter, which is the top one, and the image we want to create. So I wanted to see if I could design an algorithm that would convert that into that, a machine learning algorithm, because I wanted to process images from the UHC filter and restore the original colours. So I needed a mapping from the top one to the bottom one. And I messed around with that and came up with this. So the top one is the machine learning algorithm, this version of that. And you can see that it had a problem with green. So these pixels are very similar to each other in colour, but some of them it turned green and some of them it turned blue. So the algorithm's not very good with green and blue, which is probably okay because most of the stuff, I think, emission nebulae aren't in that range. That means that I could have done a better algorithm if I had some images of nebulae and train the machine learning on those images. So that's Eta Carinae Nebula through the filter, and that's my processing of it, and that's what I wanted to improve. I wanted to understand what the filter was doing to improve my processing. So that's my entry last year in the photo competition, and it's not using PixInsight or anything like that, and it's not using anything mathematical. So I thought, what happens if I put this image through my machine learning algorithm? And this is what we get. So the green was a bit of a problem.
The machine goes to go back to school.
Go back to school, yeah.
Could be submitting to a different type of competition.
Yeah.
This is the Trifid Nebula without a filter. What you can do is simulate the light pollution by removing all the stars, removing the nebula, and just having the background, which is theoretically the light pollution. Filling in the gaps where the stars were and filling in the gaps where the nebula. So that should be black, sort of by definition. So I said, what happens if I create that model of the light pollution and subtract it from this image? So this is what it looks like with the filter. And then if I do the subtraction process, not on this one, but on that one, I subtract the background from this, then I end up with that. And that's what people do in PixInsight. So my conclusion is probably that you can get a long way in PixInsight.
You can achieve some more progress with Photoshop as well for those who are just not going to have PixInsight. There are some plugins that will assist with that process. So you can, but it does seem like a better mathematical process available there. Yeah.
So I think it would be better starting PixInsight from this image, easier, than from starting from this image, which it looks better to the eye, but it looks like more contrast, but you have to colour balance it. And if I applied my algorithm, it would come out green. And I could work on improving the algorithm, but I don't really see the point, because I think there are simpler ways of doing it. So my conclusion is that particular filter, this particular type of image, isn't really that useful compared to what you can do in software.
Awesome. Yeah, I mean, I begin from the stuff you were sort of showing. I begin to think there's kind of a switchover point where, in terms of faintness of the object and the amount of light pollution, if you have enough image in comparison to the light pollution to get a decent looking image out, then you're wasting your time with filters maybe. You know, if without filters you can get enough contrast out of the image to be able to allow the software to suck the image out, you get somewhere. If your light pollution is really bad, and then you're probably never going to even reach that point, because your light pollution is going to blow the image out before you get enough of the actual data. At which point the filters may give you an image where you have trouble with colour, but they do give the opportunity to find the fainter object. You know what I mean? So I think there's some point in the curve between light pollution and the faintness of the image. There's going to be a point where the filter becomes a good approach, and there's going to be other points where the processing straight from a light polluted image that doesn't look as good to you, as you say, is the right approach. So if you're doing M83 from a reasonably sort of the darker end of the suburbs, you're probably better off with no filter. If you're doing the Lagoon Nebula from a very light polluted place, then you may be much better off with a filter, because you're going to be able to get those faint items out, whereas you're never going to get them with light pollution. So there's a point at which the two approaches work. And definitely in this case, there's no question about it. It looks better. I totally agree.
This isn't really a fair comparison, because I haven't done any processing.
No, of course not.
Image.
And there is definitely more contrast there, which is real. But as you say, the colour cast is not, it's not tint, after all, your filter is not tinting the image to a colour, it's removing light. And it's removing light from the stars, it's removing light, which is not a huge problem for some of your nebula, because the light you're removing is just not in those bandwidths that are coming from the object anyway. But if you're doing galaxies, then you're removing light from the galaxy just the same as you're removing from the light pollution, no question. So galaxies and things like that definitely have the filters have much more trouble with, because they're more of a broadband object. I mean, the galaxy is a broadband object. So yeah, if you use a light pollution filter on galaxies, you're removing light from your target as well as removing light from your background.
Yeah.
If you're doing it on a emission nebula, you're not really removing very much light from the emission nebula with a filter, because it doesn't emit in that range, assuming the filter is well designed. So, you know, yeah, well, I think there's some really interesting points coming out there.
I was just going to say, there's like a clear distinction that we need to make, is that light pollution contributes in terms of just the intensity of a given pixel, and there's also a spatial problem. So like, you're going to have gradients from light pollution,
Yeah.
and that's what the subtraction method that he's just demonstrated will do wonders with, and that's what happens in the pixel set with DB or AB. Creates a spline of the background and subtracts it.
That's
But
very good.
the only point at which processing won't help you is where the light pollution is quite literally overpowering your incoming signal light at the given wavelength, is what you're trying to say.
Yeah, so definitely, there are objects, galaxies seem the worst case,
So
where
like,
trying to
magnitude 16 or something.
yeah, you usually can't process that out, because it's just
You're not
swamp.
capturing, yeah.
So you, at that point, filters maybe a definite go-to. You want to go out and image galaxy clusters from anywhere that isn't really dark, and you're not going to get anywhere trying to suck the data out with the software. But when you're doing as you say, you're doing mission nebula, then yeah, you're going to get good images out without. Yeah, definitely. Oh. Well, thanks everybody. It's been definitely interesting to have